fluxes over the whole surface. I gotta add all of them. If I don't catch all of the field lines with my surface, then it's not helpful. I need all of them. So if I only get part of them, then I'll underestimate my flux, I'll underestimate my electric charge. So I just gotta account for everything. Gotta round up the cats. And what we're left with then is that this flux value, now we can express it in a little bit simpler way, or at least as we've already described it. I can evaluate every segment of the electric field with its scalar product dA over the entire surface. And this is what Gauss's law will look like for that enclosed surface. The amount of charge will ultimately have an associated flux, and they're related by this constant.
So could you say what that means again? The flux equals.
So this is the flux is the flux associated or passing through, flowing through the segment dA. So I'm going to call it field flow. Through the surface segment. I just have to add them all up. If it's regular, life is good. If it's not regular, then I have to split it apart into small pieces so that I'm only looking at the regions where E is effectively constant, or the limit is where it's constant to dA. Unfortunately, that's only for that one little piece. When I evaluate over the whole thing, then E will vary as my with both magnitude and orientation with respect to dA. Okay, so it just becomes this flowing calculus type of problem. Now, in this case, this Q is the enclosed charge. Okay, I'm not going to write the enclosed separately, but it's the amount that's physically enclosed. I don't care about all the other charge around it. Okay. Now, if this were a closed surface, let's think about this for a second. If there was an external electric field, if I took the same surface and put it with or without this charge, if I put this in that original electric field, whatever flows in is going to continue flowing right back out. So there's going to be no net flux through a closed surface unless you have a charge inside. If you don't have a charge inside, any field line that flows in is going to flow right back out. And the total flux adds up to 0 unless you have charge inside. You have to have a source inside. That's a key piece. Does that make sense? It's important that makes sense, because if it doesn't, then we have other concerns. So, this is the idea. What does it mean? Again, charge is a source of flux. The total amount of charge is limited, the total amount of flux is limited by the quantity of charge. Gauss's law says that if you basically account for all of the flux, that will always be equal to Q with this epsilon. Okay? So it really defines the very nature of charge and its relationship to how electric field substance flows out of it. So, okay, that's fine and good and dandy, right? So what does it mean? Look at a simple example, one that we've already seen, and we'll sort of see. So unto itself, it's a physical concept, kind of like the second law of thermodynamics. It's kind of important to sort of have a sense of what it means. I mean, intrinsically, it says something deep about the nature of electric charge and deep about the nature of physics itself, right? Calculations notwithstanding, that's what it is. Okay? So there's that. But there's another issue that is oftentimes helpful. As engineers and as sometimes problem-driven physicists, that's all fine and good. Second law of thermodynamics, great, heat flows from hot to cold. Newton's third law, you push on something, it pushes back, okay, you've got forces in pairs, that's whatever. But here's where the application comes in. For certain charge arrangements, you can use Gauss's law to either determine quantity of charge from flux, or, on a more practical level, electric field itself. If you can calculate the electric field for a given quantity of charge, guess what? Now you're the first step to looking at what happens when you put an electric charge there and how that charge is going to respond in the presence of that electric field. And that's really where it all began, right? Something, how do you disturb it? When you disturb it, how the hell does it react? How does it respond to that change? Okay? So it all comes back to the electric field. Gauss's law becomes helpful in calculating electric field. And I'll say easily calculated, at least compared to Coulomb's law. Coulomb's law is always correct if you can figure out how to calculate or account for all of the charges at some point in space. But you can always do that. It's just not always pretty. So let's look at the point charge, and we'll get a specific example. So let's look at a single point charge. Q. And let's give it a value. Some value. And the question is, if I've got Q here, what is the electric field at some distance away from this point charge? Now, understand, it's only the electric field associated with the point charge. If there's an external electric field that's also present, then Gauss's law does not account for that. It only accounts for the relationship between flux, electric field associated with a specific point charge, or a specific subject charge, if you will. It's not a point. So, what is E as a function of R? And that would sort of be the basic question. I'm out here somewhere, at a distance R away. I want to know what E is here. So the way the approach works is you take the charge and you establish, based on symmetry, what is an appropriate surface. So first thing we better do is establish an appropriate Gaussian surface. The term Gaussian just means it applies to Gauss's law. We call it a Gaussian surface, but it's basically an enclosed surface that's useful. Well, since we know something about the electric charge fundamentally, and even if we didn't, we might make some basic inferences. If this is a point or a spherically symmetric charge region, no matter where I am at that same distance away, the electric field will have the same magnitude, regardless of where I am. So, first thing I might do is say, well, if I make a sphere, so sphere surface or spherical surface with radius r, not big R, big R, centered at the point charge. Call that a Gaussian sphere. So in this case, I'm going to use a sphere. And at a distance r away, the area of the sphere is going to be related to 4 pi r squared at any particular distance r. According to Gauss's law, whatever this charge is inside, now maybe I will call it enclosed, it should be equal to the total electric flux times epsilon naught, or in this particular case, epsilon naught times surface integral of E dA for every point along this sphere. But here's the thing. No matter where I am, if I have a little surface over here, dA is pointing radial. With respect to Q, right? Every surface is going to be pointing out. And not only that, whatever the magnitude of the field is, it's also going to be pointing in the same direction. E is going to be constant over all of dA. So for every dA, E is constant. In orientation as well as in magnitude. So this then reduces nicely to E evaluated over the integral dA. Cosine goes away, so I'm just going to ignore it. I'm going to treat it as now a scalar calculation. And this in turn becomes epsilon naught E at this particular distance times the area of the sphere. And we know that. Enclosed, E and C. And again, I just got done saying I wasn't going to use it, so if you can just remind yourself that this enclosed cube just corresponds to the surface in question, the use of the extra subscript is not specifically important at all. It's just the surface corresponds to what's inside. Okay, so then what this tells me, if we piece all of this together and I'll start erasing some of this other stuff, you can see the integral goes away for one thing. So life is good. We can always calculate that integral, but we don't need to because we've already made some symmetric arguments about this previously with Coulomb's law in the first place. But what this leads to then is that the electric field should be related to Q over epsilon naught times the area of this sphere at this particular distance, which should be equal to Q over epsilon naught times 4 pi r squared, or rewritten maybe 4 pi Q over 4 pi epsilon naught r squared. Oh, how convenient. So the electric field at some distance r related to the charge enclosed. This just reduces right back to Coulomb's law. Okay. So that's sort of the first thing. If it doesn't fit with empirics, or the empirical observation, Coulomb's law is very empirical, then it's sort of not particularly useful. So fundamentally, we start here. Now obviously in this case, we might as well just use Coulomb's law in the first place and not bother with it. But there are advantages to using this before we take a break. So now you can calculate. If we know what R is, we can calculate all of this stuff. We may also note that the electric field at any point R, then, is going to be related to this stuff. Pointing in the direction of R, since dA will always be related to dA R, wherever it's located, and E will always be related to whatever its magnitude is in the R direction for a point charge. It isn't always as easy to just make this inference, but we can say this for this particular case. There's your Coulomb's law. So let's take a break now and just sort of absorb a little bit of the esotericity of this, as well as the utility of it, and look at some specific cases that extend. And we've already talked subtly about some of these extensions, but we'll use Gauss's law as a foundation for some of these other extensions and what they might mean. Okay? So let's take a break.